right, yeah. So, so my name is Purvi and I work at the Indian Institute of Science in Bangalore. I broadly work in several complex variables and it's my pleasure to be here. It's a beautiful campus and it's my first time in Lebanon. So I have created a very modest website for this course and I think Florian has already posted the link. So what is available over there are some assignments. So for each lecture I'll post a few problems. I'll also post some lecture notes, like after each lecture I'll post a lecture note or something like that, and then there are some references, and this is a very, very vast topic, so it's just a few references, and I might also post some extra notes depending on how the lectures go. So the title is Approximation Theory and Complex Analysis. It's very broad. So what is the oh, by the way, if you have questions, you can interrupt me during the lecture, or you can also ask me during like coffee break or lunch break or something like that. Right, so what is this course about? So I kind of want to start with a prototypical statement. I mean, one has to necessarily almost start with this statement in any approximation theory course. So prototype, and this is of course the Weierstrass approximation theorem, which is when this whole pursuit of these kind of results started. So I'm going to write the sort of the most elementary version. There are many advanced statements out there, but let me write the most elementary version over here. So let f, this is a real valued continuous function. So I'll often use fn for function. Then given epsilon positive, there exists a polynomial, which here means that it's a function of the following form. So I have aj xj, j runs through some finitely many positive non-negative integers. So here aj's are real such that if I look at the gap between these two functions, and here by the gap what I mean is the supremum over all input values in 0, 1, this is at most epsilon. Okay. So the reason I've written this statement down over here is because it sort of tells us the typical format of any sort of approximation theoretic result that you might see. So what we have over here is that there is an underlying set. Okay, so that's one of the pieces over here, and then there is some space of functions on that set. So for that we are looking at continuous functions. So this is some space that we want to study. We want to study its properties, and then there is some subclass which here turn out to be polynomials, which are somehow easier to work with. Maybe they have nice representations, they're simpler to understand, and we allow ourselves an error. And we say that up to certain error, if we can find something in this simple class that looks almost like the functions we want to study, then we are in good shape. And of course, the fourth element over here is how we are measuring the error. So here we are measuring the error in this way. This is a norm over here. So these are sort of the four components of an approximation theory result, or at least these are the kind of results that we will see. So what are we going to do? So we are, of course, so before we get into that, my first sort of reading exercise for everybody, I'm hoping that everybody has seen this result before. If you haven't seen this result before, it's important that each of you should know at least one. So there are many proofs out there of the Weierstrass approximation theorem. In fact, later in a sort of more general setting, we will actually get to see the original proof of Weierstrass, but there is also a constructive, so on the course page, maybe I will post. So there's a constructive proof by Bernstein, and what I will post is actually a nice probabilistic interpretation of that proof. So what is interesting about this proof is it actually gives you a recipe for this P. Okay, and that recipe is quite significant actually because it involves what are known as Bernstein polynomials, and you can use Bernstein polynomials to construct what are known as Bezier curves, and these are heavily used in computer imaging. So they essentially rely on this formula of Bernstein over here. So I'll post this on the web page, but you should know at least one way of proving this version of the Weierstrass approximation theorem. All right, so what are we going to do? So for us, we kind of are interested in heading towards complex analysis. So for us, the underlying set will be some compact subset of Cn. And one can, in many situations, replace this with some complex manifold. You can also consider other kinds of subsets. I mean, why compact? But I mean, I just have to focus on something. So we start with compact subsets of Cn, and then I will sort of list a bunch of function spaces that we might be interested in. And we will talk about various approximation theory results in that context. Okay, so the first space is the space of complex valued continuous functions on K. Okay, and here I will use the sup norm. So what is this? We've already come across this. This is the sup norm on CK, and this is how we are going to measure the error of approximation in this course. Okay, and of course, at this point of time, it might seem like an arbitrary choice, why this is quite a strong norm. But sort of we are sort of interested in doing this in the complex analytic setting. And a result that you might know is that if you have uniform convergence on compacts in open sets, then that sort of preserves holomorphicity. So we are kind of interested in doing approximation where we preserve the category of functions that we are working with. And so this is a good norm from that point of view. But you can, of course, ask for approximation in other norms that is completely legitimate. Okay, so let's sort of now, everything I write down is going to be a subclass of CK over here. So it's important that we are working with complex valued functions. So AK over here, and here, this is sort of useful when you're often thinking of K. So I'll try to use some other colors if I can remember to do so. So here, this is quite useful if you're thinking of K as sort of the closure of some bounded domain. So here U is, let's say, a bounded open set in Cn. And you take its closure, and so that's maybe what I'm thinking of over here when I write down this class. And so what is this? This is all those continuous functions on K such that F is holomorphic. Red is not good. The interior of K. Okay? So that's AK. But this is sort of quite a delicate class to work with. So we kind of work with something which is a little bit easier to wrap our heads around. So what makes this delicate is that when you sort of head towards boundary points, you're losing holomorphicity over here. Holomorphicity is great. Continuity with respect to that is quite, it's too flexible. So you're losing holomorphicity at those points, which makes approximation theory quite delicate for this class. And so you kind of, maybe if you sort of fail on this front, you say, okay, let me give myself a little bit more. So here, I allow myself those continuous functions which kind of extend holomorphically a little beyond the set. So F extends holomorphically to some neighborhood, open neighborhood of K. And the key thing over here, by the way, is that, of course, this neighborhood depends on the function. I'm not saying that there's a common neighborhood on which all of these functions live. It's just, you just have to find some open neighborhood where this admits a holomorphic extension, okay? By which I mean that whatever that neighborhood is, there's a holomorphic function over there whose restriction to K is exactly this function F over here. That's what we mean. Okay, and so these are all, this is a vector space, and these are all subspaces of this vector space. Something that, you know, if you're seeing these things for the first time, something that you might want to ask yourself, not only is this vector space, we have a norm on it, are these closed subspaces of those vector spaces, okay? So these are all, you can check that these are subspaces, but you have to sort of ask yourself whether they're closed or not. All right, so these are the kind of objects that we are generally interested when doing complex function theory. Now, what are the class of objects that we would like to approximate these functions by? And so that allows me to introduce some more spaces. So I'm going to use this notation P of K, which is, so I restrict, okay, maybe I didn't plan this that well, but okay, that's fine. Let's just stick to this. So I have P restricted to K, where P is a holomorphic polynomial on Cn. Okay, so that's a class that would be, it's very nice. And just to be completely clear, because we will use this notation even in the assignments, I will sort of try, in the assignments I will use the notation that I have introduced in the lectures, and I'll also try and be consistent with Michael's notations if I need to talk about forms at some point of time. So just, so I'm also going to use, by the way, this definition is not yet complete. There's something missing over here. I'll come back to that. But let me also sort of introduce this other notation. And these are all holomorphic polynomials. But rather than write them like this, I'll just sort of remind you what I mean by that over here. So these are all objects of the following form. So this is one place where I'm going to depart from Michael's notation. So I am going to use subscripts for the note, because we are not doing differential geometry in this course. So I am going to use subscripts to denote my coordinates in Cn. So here, so what are these holomorphic polynomials? So these are polynomials in Z1 to Zn. And then there are some coefficients over here that depend on, of course, these powers, and then J1 to Jn are non-negative integers which add up to some finite number. So this is what we have, and here these coefficients are, of course, complex numbers. So these are what I mean by holomorphic polynomials. The reason why I'm making a little bit of a fuss about this is because if you don't specify that they're holomorphic polynomials, Cn is R2n, and in general, one might also see Z bar, Z1 bar, Z2 bar terms. So by holomorphic polynomials, I don't have any conjugate terms over here. Okay, that's the important part. So these are my holomorphic polynomials, and then this class over here, I'm taking them, I'm restricting them to K, so I get a bunch of continuous functions which are restrictions of polynomials. Okay. But, I mean, it's very ambitious to expect that everything here or everything here or everything here can be approximated by things like this. We will, in fact, see examples where this does not happen. And so we also say, okay, I mean, we also have another nice class. Oh, I had promised to complete this definition. So what is missing here is, I mean, it's not missing, but it's more standard not to denote this subspace by pk, but what we are really interested in is we are interested in approximating things by polynomials in this norm. So we'll take the closure of this space with respect to this norm that we have introduced on K. So this is the class of those continuous functions on K that are uniformly approximable by restrictions of holomorphic polynomials. So that's what I mean by pk. Okay?
In your red definition, n can be anything you like.
Yes, thank you. Yes, good. So M, that I guess now it's complete. Well, I've also been a little sloppy in that I have not told you what. Let's write it this way. Okay, I think now it's yes. Yes, so we are allowing polynomials of all degree. And then the final class that I will write down is Rk. So let me write it like this. These are those continuous functions on K such that there exists holomorphic polynomials Cn such that R can be written as P over Q, and Q is non-vanishing on K. So I want rational functions. I want rational functions on Cn which have no problem. They are nice and holomorphic on K. So all the problematic points, they're sort of off of K. Okay, that's the point over here. And again, what I'm really interested in is the set of those functions which are uniformly approximable by these. And so I take the closure of this set with respect to this norm that we have fixed. And that's really the only norm that we will study in this set of lectures. Okay. So let me point out a few things over here. So we have some obvious containments over here. These spaces are closed by design. I've taken their closure in the sup norm. Okay? You can go back and think about this. This is not closed. So I'm just going to take its closure in the sup norm. And then I have this, and then this is contained, of course. All of these are subspaces of this large space that we started with. And what we are interested in is these are the kind of things we are interested in, and we want to know how well can they be approximated by these spaces. So we will really do two types of approximations. We'll talk about two types of approximations, both in one dimension and higher dimensions. The first is what I will call the Runga type. And as I said, this is a slightly less subtle space than this. So this is kind of maybe an easier problem. And so you're trying to understand when you can actually make one of these an equality. And then the other type that we will study is the Mergelyan type of approximation. And I will take certain facts for granted, but I will also try to prove some things. And there are lots of kinds of approximations that I will not mention at all. And sometimes I will also maybe try to choose proofs that are more accessible, but then they're also longer. So I may not always go for the most sophisticated proof in the hope that maybe something is more revealing about the longer proof.
What about AK? Is that one closed?
AK, yeah. So, well, that was my exercise for everybody. But so, yes. Which is why I'm writing it like this. Yeah, we sort of gave it away, but that's okay. There are many exercises. So, right. So this is what I had said at the beginning about why we are sort of choosing this norm, because it's sort of good at preserving holomorphicity, at least on the open part. That's kind of the convenience that we have. Okay. Any other questions? So by the way, in this language, what we are saying over here, in this language, I suppose, okay, I don't want to say this right now. So what did I want to say? So yes, so let's start talking about the Runga type approximations. And of course, there's going to be a marked difference between the one variable case and the higher dimensional case. And I'll sort of talk about both. But let's start with some simple examples. So a lot of times, I mean, you have a lot of abstract proofs, these abstract approximation theoretic proofs. But from the point of view of applications, ultimately you want to be able to find good approximations. So at least in simple settings, we should have some good recipes. So the first one is, again, of course, an exercise for you. Because the way we wrote the Weierstrass approximation theorem, it was about real valued functions, and we were approximating by real polynomials, and it seems like we completely changed our setup after that. But you should check that, in fact, that theorem does tell us sort of the best possible approximation over here. By the way, I did not say this, but this becomes an equality if there is no interior. Right? So when we're talking about Mergelyan type of theorems, whenever the interior is empty, we're actually talking about a Weierstrass kind of a theorem. That's what we are really doing. And so here, what we said in Weierstrass is really this statement. Again, I will often write these approximation theoretic statements now in this form. All right. So sort of first new example, what is this notation? This is the closed unit disk in C. It's the set of all those complex numbers which in absolute value are at most 1. And so my claim is that if I take, and look, we are doing Runga type of approximations, okay? So this statement, of course, implies a Runga type of approximation, which is that all holomorphic functions should be approximable by holomorphic restrictions of holomorphic polynomials. All right, so what is my claim over here? So if I take, my claim is really that O of T closure is in fact sitting inside P of T closure. So what does this mean? Here's a sketch of the proof. I take a function which is holomorphic on D closure. What does that really mean? It means that F is holomorphic on some disk which is slightly larger than the unit disk. So by the way, notation, I should keep track of all the notation over here. So I introduced declosure. You sort of know what this is, hopefully. This is the open unit disk in the complex plane. And so I've sort of stretched this disk out. So because F is holomorphic in some neighborhood of declosure, so that means I can find a slightly larger disk on which F is holomorphic. Now this is a one variable complex analysis fact that if you have a holomorphic function on this disk, then you have a power series expansion, and that power series converges uniformly on compact subsets. So what does this mean? That this means that I can write Fc as a power series that converges uniformly on compact subsets of this slightly larger disk. In particular, declosure is such a compact subset of that disk, right? And so now take truncations of this power series as your approximating sequence of polynomials. So this is a very simple proof of the fact that you do have polynomial approximations of holomorphic functions on the closure of the unit disk. Okay? Okay, so I'm going to erase all these spaces, and I should also now, usually when we give an example, we sort of also immediately have to burst the bubble and say, okay, but that's, this is a really nice situation. What can prevent this from happening? And so we also take a quick look at an example where this is going to fail, at least the way we want it to work. And so example 3, so my K over here is the boundary of the unit disk, which I'm sort of maybe repeating here, but it's worth going over this. So this is the boundary of the disk. It's the unit circle in the plane. I want to take a continuous function, and I'll take a specific continuous function. I'll take 1 over z. This is definitely continuous on K. It is, in fact, a rational function which has no problem on K. And my claim is, so in fact, okay, let's stick to the class that we care about. So for Runga type approximations, we care about O of k. So let's just focus on O of k. So 1 over z is definitely holomorphic in a neighborhood of the unit circle. It's in fact holomorphic everywhere except at the origin. So this is fine. And I'm saying that there's going to be a failure of approximation over here. So suppose there exists a sequence of holomorphic polynomials such that, and more notation, but I can easily tell you, I mean, maybe not many people like this, but I will still use it because it's convenient. So 1 over z on the boundary. So what is this notation over here? What does this mean? Well, it just means, I was told to use this red. So this is just going to be my notation that limit n tending to infinity, the sup norm is equal to 0. Okay, and so this is my notation for uniform convergence. I'm going to use this throughout the lecture, throughout the course. All right. So suppose we did have something like this. Suppose we did have polynomial approximability of this function. Now, the great thing about uniform convergence is that it behaves very well with respect to integration. So I'm going to integrate both sides on the set K. And so when I do that, this is on the boundary, then I should get this. So I'm integrating with respect to dz. Cauchy's theorem from one variable complex analysis tells you this is 0. This is residue calculus. This tells you this is 2 pi I, right? So there is a contradiction over here, which means that we were not right to assume that that is approximable by polynomials. Of course, this itself is a rational function. So while p of k doesn't quite do the job over here, we will see later that r of k will do the job in this setting. So, you know, the difference between these two examples, I mean, we had the closed unit disk and then we had the boundary of it. There is an obvious difference between the two, and that really sort of is really the only problem in this entire subject. I mean, this particular kind of approximation that we are trying to do over here. Questions about the examples? The difference is?
Connectness. It's
simply connect. Right. So exactly. So there is this sort of hole over here, which is.
In higher dimensions.
So that is the interesting part, right? So it's always, the answer is always more complicated in higher dimensions. Yes. So hopefully I'll be able to say at least something about that today, and then a little bit more about that later. Okay, so let's state the theorem, which you sort of have already predicted, theorem 1, and this actually is from the same year as Weierstrass approximation theorem, and this is a one variable result, be a compact set as always. The first statement says that you don't need any condition if you're simply looking for rational approximations. Okay, this works on every compact set. There is a finer version of this that can be made. Something we can say more over here, but we won't. And the second one, which is something that we have focused on more in our examples, is polynomial approximability. And that is completely characterized by the absence of any holes is connected. So the complement of this compact set in the complex plane is connected. That completely characterizes being able to approximate holomorphic functions on K by holomorphic polynomials. And what I want to talk about, so I'm not going to immediately jump into the proof of all of this. Maybe one part, I want to talk about one part because that motivates what we want to do in higher dimensions. So for now, we will skip this rational approximation. We'll skip this. Sorry, I will not use this red, but I'll use this. And what we will do is, so the sufficiency over here, there's a version of this in higher dimensions, so we will sort of do this later for all dimensions. So I'll sort of give a more general proof in all dimensions, which will sort of include this direction. And what we will prove now is the fact that this is a necessary condition for this kind of approximation to take place. Okay, so and then that's the piece that we can examine a little bit in higher dimensions as well. We can sort of think about if we want this condition to hold, what is it that we should expect out of the set K over here? And I'll go over there because there's more space over here. All right, so we'll go via contradiction. So suppose O of k is in P of k, but C minus k is not connected, i.e. C minus k has more than one connected components. So your exercise is a little bit of topology over here. Convince yourself that there is at most one unbounded, there is only one unbounded component. Of C minus k. Okay, what do I mean by unbounded component? That it does not contain, it's not contained in any ball. Okay, large, as large as you want. So that means, so if we have assumed that there's more than one component and only one component can be unbounded, that means there must be a bounded component. So let U be a bounded component of C minus k, i.e. there exists a large disk, so there exists a R positive such that U is completely contained in R times the unit disk. Okay, that's what I mean by a bounded component. Also note that the boundary of U must lie inside the set K over here. So let's just quickly run over this argument. This is important. So I have this bounded component U, and I'm saying that remember U is a bounded component of C minus k, and I take a boundary point. A boundary point is something which is a limit point both of U and of the complement of U over here. Suppose Z, and I'm going to only say this argument verbally, I'm not going to write this down. Suppose this point is not in K. Remember, K is a compact set, so it's closed. Therefore, this point is in the complement of K, which is an open set. So there is a small ball around it, which is completely inside C minus K. It's a connected ball, so it has to be in one of the connected components of C minus K. But being a limit point of U, it contains elements of U, so it has to be in U. But then that implies, so what we've got is that this little ball over here has to be in U, but that implies that B is inside in the interior. I mean, U is an open set. So Z is not in the boundary of U. It is not a limit point of the complement of U. And so that means that every point on the boundary of U has to be in K, which is crucial to complete this argument. So how does the argument go? So I'm trying to get a contradiction. I'll choose a point, I'll choose an arbitrary point A over here. So let A be in U, let f of Z be 1 over Z minus A. This should just remind you of the example that we just did. We were working with the unit circle and we had looked at the function 1 over Z, so A was just the origin over there. We are sort of just doing the same thing, but we have to use a slightly different argument in this case because there we were sort of integrating on K. We don't have any handle on the structure of K. So I don't know if there's a nice curve over there that I can try and integrate along. So I cannot use exactly the same argument, but the principle is the same. I have this point A. It is not inside K. So when I look at this function, this is holomorphic on some neighborhood of K. In fact, it's holomorphic on C minus A, which is definitely an open neighborhood of K. So we have assumed approximability. So that means that given epsilon, there exists a polynomial such that when I look at P epsilon of Z minus 1 over Z minus A, when I look at this on K, this is at most epsilon. Or let me rewrite this. So let me rewrite this. This is also the same thing as saying, this implies the following. So I'm going to multiply all sides by Z minus A. So this is true for all Z in K. In particular, this is true for all Z in the boundary of U because the boundary of U lies inside K. And moreover, remember that capital U was in this large disk over here. So the distance between, so Z is on the boundary, A is somewhere here. So the distance between Z and A can be at most 2r. So this is at most 2r epsilon. So we have this function over here. Let's call this g of z. So we have this function g of z. This function is holomorphic on U. It's in fact holomorphic, it's an entire function. It's holomorphic everywhere. And it's also continuous up to the boundary of U. And we have a bound on it on the boundary. So the maximum principle tells me that this estimate has to hold everywhere in U. This is from the maximum principle. Remember, epsilon was an arbitrary constant over here, which I can choose later on according to my convenience. But A is a point in U. So if I evaluate this function at z equal to A, this is going to drop out. G of z in absolute value is 1. And surely I can take epsilon small enough so that this is violated over here. Okay, so this violates the maximum principle. So let me just complete this here. But G of A in absolute value is 1, which is going to be larger than for small. So this is going to lead to this contradiction, which tells me that C minus K has to be, which tells me that this approximation cannot hold if C minus K is not connected. Okay, let me just pause briefly and see if there are any questions because I want to make some remarks about this proof over here. Sorry, what did I do? Okay, right. Thanks, yeah. Okay, so let's say that we forget about the rest of this theorem and we only care about this necessary condition for this approximation to hold. What about this argument in higher dimensions? You know, what is the problem over here? So let me write this down as a remark somewhere. I guess I can do that here. By the way, if you're not satisfied by the fact that I haven't proved Runga's theorem, any of these statements, I think in all the references that I have mentioned on the course web page, you will find proofs that are specific to the one variable setting. In the interest of time, I just decided to skip the one variable proof. There are many proofs out there, and it's definitely worth your time to take a look. But I want to sort of switch to higher dimensions. So let's ask ourselves, if I assume this, do I still have the same sort of statement? So remark. So this argument, I'm not saying the statement, but this argument won't work when n is greater than 1. And why is that? What is the problem over here? Yeah, so we have, you know, this construction over here. So poles, we know that zeros and poles are not isolated when n is greater than 1. So it's not clear what you're going to replace this function with, and it's not just a failure of the argument, this statement is actually not true. So in fact, this statement, if I assume polynomial approximability, this may not in general imply that C minus K is connected. And let me give you an example where I'm of course assuming certain facts. So example, simple example is if you take K to be, so again notation, how can I avoid, okay, I'll avoid notation by doing this. So I take disk cross disk, the by disk, so I write that as D2 over here, and I remove, this is always a problem, yeah, so I'll remove sort of, I'll create a hole in that. Okay, I hope I'm writing this correct. So what I'm looking at looks something like this. This is and closure. So let's take the closure of the whole thing. Okay, and then I remove a hole, and so the compact set that I'm looking at looks like this. This is my compact set over here. Now if I take, so this guy, C minus K, has two components, because I have created a second component in this, and clearly I've created a second component. But if you take a holomorphic function on K, then, and this is a fact that I'm assuming from several complex variables, I'm not sure if this was covered in the prep, but that's fine, you can just take this for granted. Every holomorphic function that I have on a neighborhood of the set, it actually extends holomorphically over here. Okay, so that means that F extends holomorphically to D2 closure, so to a neighborhood of D2, and here it is approximable by holomorphic polynomials. Okay, so again, you can go back and think about why this is the case. Why is it that if I have a holomorphic function on the closure of the by disk, then I have approximability by holomorphic polynomials? You can go back to the way we did our second example for the closed disk. You can try to mimic that idea over there. And so what's happening is you have this holomorphic function over here, you've extended it, you have uniform approximation on this extended region. You can obviously just restrict that approximation to the set that you started with. So you do always have, what this is telling you, so sorry for the bad board work, but this is telling you that you do have polynomial approximability. Okay, so how am I doing on time? Yeah, so this is certainly not a necessary condition, but maybe I can say at this point, it might sound a bit mysterious, this is really the only obstruction in this being a necessary condition. This sort of simultaneous extension, this is really the key problem. There is no other issue that prevents this from happening. Okay, so we'll look a bit more into this later. But so what I'm going to do is, I'm going to, for the rest of the, do I have 8 minutes? Yeah. So for the rest of the 8 minutes, I'm going to stop talking about approximations, and I'm going to suddenly start talking about some notions of convexity. And only in the next lecture will I sort of go back to what does it have to do with all of this. Okay, so our goal is to try and have some version of this in higher dimensions, and currently we are quite far from that. We don't even have a good necessary condition in our hand. Okay, all right. So I'll sort of end with some definitions. And I think that's also, I mean, once I give you the definitions, that's also enough information for you to actually try some of the assignment 1 problems. Okay, so for now you just have to go with it because it does seem a little bit out of the blue. There are 2 pieces here. So again, for rational and polynomial, we have 2 different definitions. So K is a compact set, as always. Okay. So we are going to define notion of a hull, the rationally convex hull of K is the following set. So I'm sort of going to collect all those points in Cn that cannot be separated from K using polynomials. So what do I mean by that? It means that for all polynomials on Cn, whenever P vanishes at this point Z, then P has to vanish somewhere on K. So this is maybe a little hard to digest, so, and I'm also not using the correct notation, so I'm looking at the 0 set of P, and I'm saying that that must intersect this set. I'll sort of write this a little bit differently, and then I'll also explain it with pictures. But what I'm saying is that if you have a holomorphic polynomial that vanishes at this point, then it must vanish on K, which means that I do not have any holomorphic polynomial that vanishes on Z but does not vanish on K. But let me write it a little bit differently if this is confusing. This is actually equivalent to saying the following, that if you hit this point with the holomorphic polynomial, then this lands in the image of P, in the image of K under P. Okay, so if you, and this is true for all holomorphic polynomials. So just using holomorphic polynomials, you're not able to, on the image side, you're not able to distinguish Z from K. Sort of Z keeps getting put inside K when you hit it with holomorphic polynomials. Those are the set of points that we kind of care about. And maybe I wanted to say something. Did I want to say something else? Okay, so maybe before I.
Why are you calling it rationally convex?
Yeah, so that's the great mystery over here, which I will clarify after I introduce polynomial convexity. The cop out, I mean, I could sort of give you a silly answer, which is that I would get a Runga approximation theorem of this kind if I assumed rational convexity. But I think there is a better reason, and I'll come to that. Yeah, so what does this have to do with any of this? But more importantly, so whenever there is some notion of hull, there is of course a corresponding notion of convexity. We say that K is rationally convex if, so it's clear that capital K is always inside the hull, but if you get nothing more, then we say that the set is rationally convex. And of course, there's currently, I still haven't given you a reason for why we use this terminology, but I'll give you a picture to begin with, which might clarify some of these definitions. By the way, the fact that these two are really saying the same thing, you kind of need to go and make a one-line argument over here that these really are saying the same thing. And so let's draw a picture. So a set K is rationally convex if it coincides with its rationally convex hull. What that means is that if I take a point outside it, this point is not going to be in the hull, in the rational hull. And what does that mean? It means that you can find some polynomial, let's say Pz. So there exists some polynomial that depends on this point. And if you look at the zero set of that passes through, so this is Pz, the zero set of this polynomial. It passes through this point z, but it does not pass through k. So this is what I mean by separating this point from the set. And so you can do this for each point. That is a complete characterization, or that's really the definition of rational convexity, sort of presented in terms of pictures. Okay, so this has something to do with approximation, which I will not tell you right now. And then there is a version of this for polynomials. So the polynomially convex hull of K is the set, and here I'll use K hat. The notations do vary in the literature. I'm just sticking to something. This looks a little bit different. You take those points where some sort of maximum principle is satisfied. So we have already encountered maximum principle when talking about approximations. And so here what happens is that the absolute value of P of z is at most the supremum, the norm of this, the K norm of this function. Okay. And this is true for all holomorphic polynomials. Okay, and K is said to be polynomially convex if it coincides with its hull and no extra points get added to the hull. Okay, so there is a corresponding picture for polynomial convexity, which is not trivial. It's not trivial to prove. There's a certain geometric characterization using these hypersurfaces. I've put that in one of your assignments. I cannot remember if it's the first or the second assignment, but you will work out another characterization of this. But sort of to end this discussion, I want to address Michael's question about why talk about rational convexity. So if you take classical convexity, so what is classical convexity? Take 2 points and the line joining the 2 points is always inside the set, classical convexity. There is a way to define convex hulls in this fashion using real linear functions. So you can take, so let's say this is sitting inside Rn, and you can look at all those points in Rn such that if I, something like this, let me just write it like this. For all real linear, probably need an absolute value here, for all real linear functions on Rn. So this is a very common format for defining hulls, and even the traditional convex hull can be written in this format. And if you, instead of working with polynomials, if you work with rational functions which have no problem on K and no problem on Z, then you can rewrite the rationally convex hull in this form using rational functions. So you can truly reconstruct this hull using the class of rational functions. And if I did it that way, then it would make sense to call it the rationally convex hull. Okay, so I don't have now, I mean, I'll stop over here. I'll start with some examples next time, and then we need to actually understand what does this have to do with approximations.